Yo, what's up everyone? Welcome to Equilibrium Part 1. Today we're just going to talk a little bit about what equilibrium is, and we're also going to introduce the equilibrium constant. So, some reactions are going to go to completion. So if you have something like A going to B, at the start you might have like a bunch of these brown A molecules, and at the end they're all going to be B molecules. That's what it means for a reaction to go to completion, meaning all the reactants turn to products. Now, if you were to plot the concentrations of A and B over time, it would look something like this. You can see how the concentration of A is declining, and the concentration of B is always increasing. But not all reactions are going to go to completion. So if you take a look at this reaction right here, where A is in equilibrium with B, at the start you might have a bunch of these brown molecules, and at the end you might have a bunch of the blue ones, or the B ones, but you also have the reactants in the final container. So if you were to plot their concentrations over time, they would look a bit more curved like this. And you can see how at the end they kind of flatten off. And some people may expect that at this position is where the system has reached equilibrium, where their concentrations intersect, but that's not really true. Where equilibrium really is when their concentrations have started to stabilize and they don't really change as much. So essentially, in this one equilibrium expression, you have a forward reaction where A is going to B, and you have a reverse reaction where B is turning back into A. And essentially, these reactions go on forever, but there comes a point where the changes in them is very minuscule. And that's why this diagram here is a little misleading, because equilibrium is not constant. In fact, we have dynamic equilibrium. This chart kind of implies that after a certain point, the reaction just doesn't occur. The forward reaction stops, and the reverse reaction also stops. A good analogy that I think is helpful to understand this is thinking about maintaining someone's weight, right? At the core of it, like an oversimplification of weight would be calories in versus calories out. If someone has many calories in but only a few calories out, they're going to gain weight. If they have few calories in but a lot of calories out, they're going to lose weight. But if you have calories in and calories out at the same level, you maintain your weight. And that weight is kind of at equilibrium. Even though your weight is at equilibrium, it's not like you're not eating anything or you're not burning off any calories. It just means that the rate at which you're eating and the rate at which you're burning it off is the same. So we have an equilibrium of our weight. And that's the same thing of normal equilibriums. We call this dynamic equilibrium because at a macro level, if you really zoomed in here, you would kind of see these kind of like moves and these grudges where they're changing. But at a macro level, you don't notice it. Essentially, they stay the same because the rates cancel each other out. So again, at equilibrium, it's not like the forward reaction and the reverse reaction have stopped happening. It just means that they're happening at the same rate, so it appears as the system is not changing. We can have different types of equilibrium. First of all, if we have something like A to B where red turns to blue, you can have one where at the end there's a lot more blue than red. We say that the equilibrium is a lot more product favored than reactant favored. But you may have another type where C is going to D, and at the end you have a lot of red molecules as opposed to blue molecules. In this case, we call this equilibrium, or this system, we call this reactant favored. In this case, we say equilibrium is to the right, and in this case, we call equilibrium to the left. And that just means the right implies that we're more product favored, and then left implies that we are reactant favored. And so we need a way to kind of quantify this. We've been talking about this qualitatively, a lot more products than reactants, etc., but we need a way to represent this mathematically. And the way we do that is using the equilibrium constant. The equilibrium constant is a general description of the equilibrium condition. So if we had a general reaction where A plus B produces C plus D, the equilibrium constant would be C to the C, or the concentration of C to C, concentration of D to the D, and then you get the rest. And so we call this Kc because it is the equilibrium constant using concentrations. We also have Kp, which is equilibrium constant using partial pressures. And there's a relationship between Kc and Kp, which doesn't really come up a lot, but essentially it's Kp equals Kc times RT to the change in n. But what you really need to know is this general formula. This general formula is super important. This general formula right here. And that is the general formula for all of these equilibrium constants. I think in the next lesson we'll talk a bit more about different types of equilibrium constants, but fundamentally they're all the same. They're just different ones depending on what situation you want to use them in. So equilibrium constants that are greater than or equal to 1 are going to be product favored, and equilibrium constants that are like less than 1 or a lot less than 1 are going to be reactant favored. And so you might have a k that is, I don't know, like 10 times, 10 to the negative 30 or something. That would be extremely reactant favored. And you might also have a k that is 10 to the second, and that would be incredibly product favored. And this mathematical expression kind of represents why, because if you have a super positive number, then that means that this value in the numerator, the value of your products, are going to be a lot greater than the value of your reactants. And similarly, if the numbers on the numerator are a lot smaller than the numbers in the denominator, then that means you're going to get like a really small number, and that's going to be super reactant favor. Another thing about equilibrium is going to be heterogeneous equilibrium. So these are going to be equilibrium involving multiple phases. So something like if A was in equilibrium with B, but you can kind of see how it's a gas and it's a solid, and it produces an aqueous and a liquid. Well, in rate or like in equilibrium constants, pure solids and liquids are not going to count. So you can see how the B here is a pure solid and the D here is a pure liquid, and therefore it's not going to be included in our equilibrium constant. The aqueous here is included because it's not a pure solid or liquid, and the gas is also included. And you can see here that there's a exponent of 2 because there's a coefficient here of 2 on the A. And so the exponent is going to be stoichiometric. Alright, I think that's all I have to for the lesson. Let's just do a bit of practice to kind of solidify all this. The diagrams below represent the progress of a reaction A to B with molecules of A represented by solid circles and molecules of B represented by open circles. Which statement best describes the reaction at t equals 1000 seconds? Well, the important thing about t at t 1000 seconds is that it does not change from t 100 seconds. You can see that there's the same number of black and white molecules in t equals 100 seconds and t equals 1000 seconds. So this implies that the reaction is at equilibrium. And so A here, the reaction is at equilibrium because the concentrations of A and B are no longer changing. That is what makes sense. If we were to look at a microscopic level, then yeah, they would be a bit changing, but overall they would look the same because we're looking at it at a macro level. So our answer here would be A, and that is the right answer. Let's move on. Sulfur trioxide is formed from the reaction of sulfur dioxide and oxygen. At 1000 Kelvin, an equilibrium mixture has partial pressures of 562 bar of SO2, 0.101 bar O2, and 0.332 bar SO3. What is the equilibrium constant Kp for the reaction at this temperature? Remember Kp. Kp is going to be the partial pressures of the products over the partial pressures of the reactants. So the partial pressure of SO3 over the partial pressure of SO2 times the partial pressure of O2. And since the O2 has a stoichiometric coefficient of 1/2, this is going to be raised to the 1/2 power. And so if we solve for all this, or if we plug all this information in, we're going to get that it's 0.332 and then 0.562 times the square root of 0.101. And if we solve for this, let me just solve for this really quickly. 332 divided by 0.562 times the square root of 0.101. That's going to come out to about 1.86, which is answer choice A. And that is correct. So again, just knowing the formula of Kp and then being able to plug in all the information to find the answer. Pretty simple. Let's move on to the last question. Consider the reaction carried out at constant volume. For initial concentrations of SO2 and O2 of 2 molar and 1.5 molar respectively, the equilibrium O2 concentration is 0.8 molar. What is the value of Kc for this reaction? Now, the important thing about the Kc is that the concentrations that you use for them must be the concentrations at equilibrium. So currently, the only equilibrium constant that we know, or the equilibrium concentration that we know, is the one of O2. And we know O2 is at 0.80 molar. And so how do we find the equilibrium concentrations of SO2 and SO3? Well, we know that there was 0.7 molarity of O2 that was consumed in the reaction. And since SO2 is used up at twice the rate of O2, as implied by the stoichiometric coefficient here, then that means 1.4 molar SO2 is going to be consumed. And since we have 2 molar SO2 and we're using up 1.4 molar, then that means we are going to be left with 0.6 molar of SO2. And so how do we find out the SO3? Well, since we know that the SO2 and the SO3 have the same stoichiometric coefficient, that means that the amount of SO2 that is consumed is going to be the amount of SO3 that is produced. And since we know 1.4 molar was used up, then we know 1.4 molar of SO3 were produced. So we have the equilibrium concentrations. We just need to plug this into our Kc formula. And so it's going to be products SO3 squared, since we have a 2 right here, over SO2 squared times O2. And we have all these values. So SO3 is going to be 1.4 squared, and then SO2 is going to be 0.6 squared times 0.8. And if you solve for this, you're going to get that it's going to be 6.8, which is answer choice A, and that is in fact the right answer. So again, the important distinction is that you cannot use the initial concentrations. You have to use the concentration at equilibrium, which you can determine by just doing a bit of stoichiometry. All right, that was our last question. I hope you learned something, and I hope you'll join me in the next lesson where we're going to go a bit more in depth into different types of equilibrium constants. See you later. Thank you for watching.